Right, so we'll start the lecture now. So today we'll start with a new topic, which is on hyperbolic equation or the wave equation. So till now we have talked about the elliptic and parabolic equations, and this is the third topic, which is on the hyperbolic equations. And once we complete this topic, then we'll be able to combine all the terms into one equation, which is our common form that we talked about, the general common form. Right, so for discussing this, we'll be discussing the 1D wave equation. I talked about this 1D wave equation in the beginning of the course when we discussed some template equations, but I'll write it again. So the governing differential equation for the 1D wave equation has a transient term del phi by del t, and it has a term which is the convective term, which is u times del phi by del x. So here u stands for the velocity field in this case. So u is a known quantity, and we are solving for phi as a function of x and t. And here it's given to us that the velocity u is greater than 0 here. U could be less than 0 as well, but we are taking the case where u is greater than 0. Now remember, u is a scalar here because we are talking about one spatial dimension. So this is a scalar. If you're talking about two spatial dimensions, then in that case you would have u as a vector. But just to keep things simple, we'll start with u as a scalar. So that's it's greater than 0. And x in this case ranges between the complete real line. So x could be positive or negative. Time, of course, is always positive. So we'll also need an initial condition, which is the the function phi given at t equal to 0, which is at x at all x values at t equal to 0, which we'll call as phi naught as a function of x. So since it's at t equal to 0, so it's only a function of x. So that function, which is the initial condition, is called phi naught. I'll not talk about the boundary condition right now. We'll discuss it a bit later. Although you know that we do need, in this case, how many boundary conditions would you need? One. Right. So we'll talk about which boundary condition we'll need after we do some analysis. Right, so you know the exercise now. We have a governing differential equation. We have to convert that, finite difference method, so you have to convert that to a difference equation. And how do we do that? We have to use a discretization method. Well, you could use whatever method you are comfortable with. I would go for, let's say, a forward time, and I will go for backward space. Let's choose this and go ahead. So what does this become? So if it's forward time, then we have phi n plus 1 minus phi n upon delta t for the point I. On the right, and then we have plus u times, and this is the x derivative. Now this is forward time backward space. So then this phi becomes, well, they are both at ends, and since it's backward, so it's phi I minus 1 upon delta x, and this is equal to 0. Is that clear? So let's see how the stencil of this scheme looks like. So we have the point I n plus 1, that's this one, and then we have I n, which is this one, and then we have also I minus 1 n, which is this one. So the stencil looks like this. Right, so now we are quite comfortable with this exercise. Next is, well, a truncation error. Well, we have an intuition here that since it's forward time, backward space, what do you think would be the truncation error in delta t and delta x? Because forward space of forward time is order delta t, and backward space is also order delta x. So if you combine them, we can guess that it becomes order delta t delta x. So that's the truncation error for this case. Well, not an amazing scheme in terms of truncation error or the accuracy, but it's a good start. So let's, what's the next thing we'll want to check? Stability. So for stability, what we need is, we need to write the, go for the von Neumann error analysis. So in that case, what do? We write the error equation first. And in this case, you'll see the error equation turns out to be the same as the governing difference equation. So the error equation becomes so we can write the error as a Fourier series, and we check for an arbitrary Fourier term. So we have to make sure that all the Fourier terms in the Fourier series should be stable or should be bounded. So what we go for is, we take the kth wave, which is, we write epsilon ni as an e to the power of jk delta xi.
Why we can't use diagonal dominance?
Sorry?
Diagonal dominance. Why we can't use that?
Diagonal dominance. Diagonal dominance is for iterative schemes. You're confusing that. So the idea of diagonal dominance was discussed when we want to discuss the convergence of an iterative scheme. This is something else. This is for stability. Right, so for this, can you do it? Should I give you 5 minutes? Now you're experts in this. So please use this, perform the von Neumann error analysis for this equation and see where you get. So I'll give you 5 minutes to try it yourself, and then I'll do it on the board. So let's do the stability analysis. So what I'll do is I'll multiply the whole equation by delta t. Right, and then you can see that for getting the amplification factor, I'll have to divide it by an. So I divide the whole equation by an. So that gives me an here, and all these an's will vanish. Then I'll also divide it by e to the power of jk delta xi. And here in the last term we'll have e to the power of jk delta x. Right? So this will be written as the amplification factor g minus 1 plus this term u delta t by delta x. We'll denote that as nu, and then we'll have 1 minus e to the power of minus jk delta x, and this is equal to 0. So remember, the aim is to get g first, and then we need to get mod g from here so that we can check for the stability criteria, which is mod g has to be less than 1. Mod g has to be between minus 1 and 1. Right, so what does g become? So g is 1 minus nu plus nu times e to the power of minus jk delta x. And e to the power of minus jk delta x, we can apply the Euler's formula. So we can write this as cos of minus jk delta, minus k delta x, but cos of a negative function is the same as cos of the function. So cos of k delta x minus j times sine of k delta x, and this we have a complex term, so we'll separate the real and the complex parts. So this becomes 1 minus nu plus nu cos k delta x. So that's the real part, and then we have minus j times nu sine k delta x. That is the minus nu sine k delta x is the imaginary part. So mod g becomes, let's take the square of that. So that becomes 1 minus nu plus nu cos. Just to save some work, I'll write k delta x as beta. Okay, this is mod g squared. And then you can expand this, a plus b plus c squared, and then so on. So if you do that, I'll just write the final expression after you simplify this. So this becomes 1 plus 4 nu times nu minus 1 times sine squared beta by 2. Okay. So you can try it and see that you will get the same thing. So this is mod g squared. Now the condition for stability is mod g has to be between -1 and 1, right? So let's apply the condition. So let's start with this condition. Now remember this mod g is the square root of this, and this has to be less than equal to 1. Now if something has to be less than equal to 1, then its square also has to be less than equal to 1. That's the reason we just wrote this term, because if this quantity is less than equal to 1, then that implies that the square root of this will also be less than equal to 1. So this basically becomes nu times nu minus 1 times sine squared beta by 2 is less than equal to 0. So we subtract 1 from each side and then we divide by 4. So this is the condition we get. Now sine squared beta by 2 is a positive quantity, and we are saying that the left hand side has to be less than equal to 0. So the only way this can be less than equal to 0 is that nu times nu minus 1 is less than equal to 0. And this is true when nu is between 0 and 1, right? So if nu is greater than 1, then nu times nu minus 1, so nu is greater than 1, nu minus 1 also becomes greater than 0, so it becomes positive. And if nu is less than 0, it's a negative number, then nu is negative and nu minus 1 is also negative, so you get a positive number. So the only way we can get nu times nu minus 1 as negative is when nu is between 0 and 1. So that's the condition we get for the first part, which is mod g is less than equal to 1. So I'll just box it. Well, actually, yeah, this condition is not even required. So square root of that is going to be a positive number. We're taking the positive square root anyways, right? So this is the only condition that we have. So this gives us that mod g is, this gives us the condition that nu is greater than 0 and less than 1. Now nu is greater than 0 always, because the way we have defined nu, in this case, how do we define nu? Nu was given as u times delta t by delta x, right? So in this case, u was positive, so that's the reason it is, but u could be negative also, right? So this case, the stability criteria is that nu has to be between 0 and 1. So this is our delta x is always positive. The way we define delta x and delta 3, they cannot be negative. The interval size cannot be negative, but u can be negative. There's no meaning of, if I give you a line and I say you break it into n parts, you cannot have a part being negative in this, right? It can tend to 0, but it can never be below 0. So this is the stability criteria for our forward time, backward space discretization. So this condition actually has a name. This is called the CFL criteria. And this number nu is also called the Courant number. So CFL stands for Courant, Friedrich, and Louis. So these were the people who contributed to this work. So, but the number got the name from the first scientist. That's called Courant. So you'll see in software, in books, and so on, it will be written that CFL number, or sometimes they'll say CFL number, sometimes they'll say Courant number, or sometimes they'll say the CFL criteria. So all that means is that nu has to be less than 1 and greater than 0. Okay. Right. So I'll give you a homework here. Well, a couple of homeworks. The first one is you have to show that the forward time center space, which I think you were inclined to suggest for this equation, is unconditionally unstable. Of course, for this equation. So we're talking in the context of the 1D wave equation, where our u is greater than 0. Right. The second homework is to show that forward time, forward space is also unconditionally unstable. So actually we are not left with many options. It's only the forward time, backward space that is conditionally stable. The condition being that the Courant number has to be between 0 and 1.
Backward time center space.
Backward time center space, I don't think that will work. But you can check. So why is it happening? I mean, why is the behavior very different from the parabolic equation that we've talked about? So there is a reason. There is a very strong reason. So for that, we'll have to understand what is the nature of this equation that we're solving. So let's jump into that and understand the nature of the solution or the nature of the equation that we're solving. That is the 1D wave equation. So what is the 1D wave equation doing? So 1D wave equation has a transient term and a convective term. So that is, a convective term is simply responsible for letting the information flow with the velocity. Just like think of a swimming pool, and on one end you introduce some hot water and the flow is happening from left to right in the pool. So what happens is, if you introduce some hot water on the left hand side, you will see that after some time, since the flow is happening from left to right, the hot water will have moved. So the solution is simply letting the information flow from one direction to the other direction, basically in the direction of the flow velocity. So the flow of fluid, which is denoted by the velocity in this case, is transporting the phi field, whatever that is, it could be temperature, it could be concentration, whatever it is. So phi field is flowing with the velocity. That's pretty much what is happening. Okay. So it's purely convective in nature. There is no diffusion, there is no spread. I mean, if there was a spread, I will have to add a diffusive term as well. But here, if you start with a certain shape of a phi, then that shape will be retained. It will not spread in space, and that shape will simply get convected, or it will simply move in the direction of flow. Okay. In fact, so that intuition, I think, is enough for you to understand the reasoning behind only forward time, backward space working. So let's see. So let's say that you have ith spatial point, then you have I plus 1, and then you have I minus 1. And let's say the velocity direction is this, which is u being greater than 0. It's from left to right. Now if the flow is from left to right, and the nature of the equation is such that it simply transports the phi field, then what do you think that if you're trying to find the solution at this point, would it depend on the information from the left point or the right point? So the solution at the ith point at any time will depend on the solution from the previous time at I minus 1th point or I plus 1th point? I minus 1th point. That's very intuitive, right? Because the information, the flow is happening from left to right. So whatever was there at the left is now going to come to the right. And whatever was there at I plus 1 will have moved to I plus 2 and forward. So the solution value, the value of the function phi, I at n plus 1, should be a function of phi at I minus 1 at the nth time, previous time. So that means it should be a function of this. Similarly, if your flow was happening in the other way, if your u was negative, then this should have been a function of I plus 1, because now the information is traveling from right to left. So we say that information always travels from the upwind direction. So this, for the case where u is greater than 0, this term is called upwind, and this term is actually called downwind. Okay, that's just terminology, general terminology, not specific to CFD. That if you have wind blowing from some side and you're standing here, then let's say if somebody is smoking on the side where you have the wind blowing from, then you'll smell it. If you're standing downwind, if you're standing at the ith point and the wind is blowing from left to right and somebody is smoking at I plus 1th, that will not bother you, because the information will travel to the right from there. So information always travels from upwind to the downwind direction. And similarly, for u being less than 0, the upwind point becomes I plus 1 and I minus 1 becomes downwind. Now we're talking in terms of relative to the ith point. So I plus 1th point is going to be upwind for this u less than 0 case, and I minus 1th point will be downwind for the u less than 0 case. So information always travels from upwind to downwind. You can see that. Upwind to downwind, upwind to downwind. So is that clear? So now let's look at the scheme that we just wrote. This one, forward time, backward space. So what we are saying is that the information at the ith point at the n plus 1th time depends on information at I minus 1. It also has the information at ith point, which does not bother us too much. But if it had any information at a point which was to the right of ith point, then that will be incorrect, because that has no physical meaning, because the information for this equation is always traveling from upwind to downwind. And that is exactly the reason, again intuitively, that the center space scheme, any scheme that has contribution from terms coming from the I plus 1th, I plus 2th, or any downward point, will start to become unstable, because you're contributing some information which has no effect on the equation at all, or the ith term at all at n plus 1th time. Is that intuition making sense? That's very important, because otherwise we will end up doing a stability analysis even though we have an intuition that the scheme may not be stable. So what we do is, if we want to develop a higher order scheme, what can we do? Let's say we want to order delta x squared scheme in this case. What could we do? So let's say for this case where your u is greater than 0, if I had to include one more point, what spatial point would I include? I minus 2, right? Because information is traveling from left to right. So if I had to include more spatial points, I would rather include this one and not this one, because the right I plus 1th point will make it unstable. Okay? So this process is actually called upwinding. I mean, technically speaking, when the flow is happening, you don't even know what the direction of flow is. I mean, in this case, I have told you, but you may be solving another equation to get the flow field. And flow could be different in different places. I mean, if you think of a room, the flow would be could be positive here, the flow could be negative there, right? So the flow is a non-homogeneous field in most cases. If it's homogeneous, if the flow is the same everywhere, then life becomes very boring. So flow is non-homogeneous. So flow is something that changes with space. So depending on what the direction of flow is, you'll have to change the scheme there. So we use a scheme called upwinding scheme. So we say that if we are using a first order upwind, so we'll use forward time backward space wherever u is positive, and we'll use forward time forward space wherever u is negative. Or we say that we're using an upwinding scheme so that the information that is upwind is affecting the flow. So I would put some sort of an if condition in my loop, that if u is greater than 0, then phi upwind is phi I minus 1. Else, if u is less than 0, then phi upwind is phi I plus 1. Okay, and then all I have to do is, after this loop is over, I can say that my let's say spatial derivative is phi upwind minus phi I upon delta x, something like that. When we write the code, we'll write it in a more proper sense. So this is how you would have loops organized. You have to take care of a negative sign and so on, but that can be managed. Okay, so this idea is very important, and that's the reason, that's the whole origin of the up. So when you select check boxes in your software, then there'll be an option: center space, upwind, downwind schemes are also there, which are actually always unstable, but for testing and playing around with things. So you have upwind, you have second order upwind, you have third order upwind. So all these options will be available. So you should be able to understand what they actually mean. So this is what it means by upwinding. Now let's talk about boundary condition. I didn't talk about boundary condition yet, but we do need one boundary condition. So let's look at this domain. Now this is the 1D domain, because you only have x direction. So you can either have a boundary condition here or a boundary condition there. Now let's say the flow is happening near, the flow is in such that u is positive. So u is like this throughout the domain. If you had to use one boundary condition, which one do you think should we have? A left boundary condition or a right boundary condition?
Right boundary.
The flow is from left to right. So which boundary, let's say in this case flow is from left to right, so which boundary will affect the flow inside the domain at later times? The flow is from left to right. So if the information is traveling, let's think of it. So on the left side you have hot fluid, right side you have cold fluid. And the flow is happening from left to right. Is it bringing hot fluid or bringing cold fluid? Hot fluid. The hot fluid is flowing from left to right. So the left boundary condition should be specified. If you specify the right boundary condition, it will have no effect on the information. It will try to look for information which is coming from the left, but you have not specified that. So it is an ill-posed problem. So for the problem to be well posed, you have to specify the left boundary condition here. Okay. So if you specify the right boundary condition, then it becomes an unphysical situation that will make it ill-posed.
But there will be no left point at this point.
No what point?
Left at boundary condition.
Right. So I mean, we're talking about the boundary condition. So at I equal to 0, at the index I equal to 0, you specify the value. So what happens is that I equal to 1, it will need information at I equal to 0. So when we write the algorithm for this, it will be more clear. Okay.
It should be three-sided boundary condition.
It could be Neumann also, but yeah, Dirichlet is. I mean, we need the Dirichlet boundary condition for some information to be specified.
If it would be Newman only, then how we can apply the backward time?
You are right. I mean, Neumann will not work, and physically also, if something is flowing from left to right, then we need what is flowing. So we need a Dirichlet boundary condition. And all these will become critical when we solve the Navier-Stokes equation very soon, because that will have convective term as well as diffusive term as well as source term and as well as all other terms as well. So all these ideas will be put together, but some terms will dominate over the others. So we will introduce new numbers which will help us figure out the ratios of one term to the other term. Okay. Another point before we close is about the Courant number. So we said that the Courant number has to be less than 1 here, greater than 0. But let's say that now we are sure that we are applying the right upwinding, so that we'll always have Courant number will less than 1, because we'll start taking the magnitude of velocity in this case. So we'll define the Courant number as u delta t by delta x. Okay, so that definitely it will be greater than 0 always, and less than 1 is something that we have to ensure. So let's say that it was less than 1, but now what you realize is that you need the solution in later times quickly. So you start increasing your delta t, because you want if you have very small delta t, you have to take too many steps. That becomes computationally expensive. So you take a larger delta t so that you can move to a later time quickly. But if you increase your delta t, it may happen that your nu might now become greater than 1. So what do you do to ensure that nu still stays below 1 for stability? Increase delta x, because u is based on the physics, you cannot change that. So the only thing you can do is delta x can be increased. But what is the meaning of delta x being increased? What effect does it have? Accuracy. The accuracy gets decreased, because if you have larger delta x, it's like you have lesser number of points in the domain now. So you have decreased accuracy, spatial accuracy, right? So there is a trade-off again, like you had. So stability criteria always gives you a trade-off between delta t's and delta x. Okay, so that is a very strong constraint, and we have to live with it. There's nothing we can do about it. Or on the other hand, if everything is working well for me, but now I want to get a better spatial accuracy. That's what you want, right? I give you a supercomputer now. I say that, can you solve the equation more accurately? You can give, yes, I can decrease my delta. I can put more number of spatial points. But if you decrease your delta x, it might happen that your nu might become greater than 1. So what do? You have to decrease delta t. And that means that now you have to go through finer steps, very similar to what we notice in parabolic equations, when the numerical Fourier number has to be less than half. So now if you are forced to take too many time steps, and that will result in sometimes the simulation taking a very long time, just because you had to decrease your delta x, you had to decrease your delta t as well for stability. So then we might start looking for unconditionally stable schemes, but mostly this is the scheme that is still being used, because that is the most robust, as long as you maintain your nu less than 1. But we'll talk more about this in the future. Okay, so we'll stop here and I'll meet you on Thursday.